The simplest and most fundamental version of cluster analysis is partitioning, which organizes the objects of a set into several exclusive groups or clusters. To keep the problem specification concisely, we can assume that the number of clusters is given as background knowledge. The parameter is the starting point for partitioning methods. Second one is a k-means clustering. It's a centroid-based technique. Suppose a dataset D contains n different objects in Euclidean space. Partitioning method distributes the objects into in dataset into k different clusters. Third one, partitioning around Medais. Partitioning around Medais. Other name of this method is the k-Medais algorithm. The clustering method has been studied extensively for more than 4 decades and across different disciplines due to its broad applications. As a result, many clustering techniques have been reported in the literature. We can categorize the clustering methods, but it is difficult to provide the different categorization because the techniques overlap each other in terms of clustering methods. So it is not possible to cover all the techniques in this series. We are giving importance to the major techniques belong to the partitioning and hierarchical. As shown on the screen, partitioning methods. General characteristics of these methods are it finds mutually exclusive clusters of spherical shape and it is distance based. It may use mean or medai to represent the cluster center. It is effective for small to medium sized data set. Second category is the hierarchical based methods. Clustering is a hierarchical decomposition. It cannot correct erroneous merges or splits. It may incorporate other techniques like microclustering or consider object like linkages. Third one, density based methods. It can find arbitrarily shaped clusters. Clusters are dense regions of objects in space that are separated by low density regions. Cluster density, each point must have a minimum number of points within its neighborhood. It may filter out outliers. Fourth one, grid-based method. It uses a multi-resolution grid data structure, fast processing time. So the fifth one is the model-based clustering. It consists of EM algorithm, autoclass, cobweb, and ANN clustering. We cover the following clustering techniques only. In the partitioning-based method, we cover the k-means algorithm and partitioning around Medaites. Second category, hierarchical methods. Diana, the divisive analysis. Second one, Agnes, agglomerative nesting algorithm, and the rock. Third one, density-based algorithm, DB-scan. K-means clustering algorithm are proposed by Hartigan and Wang in 1979. Given a set of n different objects, the k-means clustering algorithm partitions the objects into k number of clusters such that intra-cluster similarity is high, but the inter-cluster similarity is very low. In this algorithm, user has to specify the k value, the number of clusters, and consider the objects are defined with numeric attributes and thus using any one of the distance matrix to demarcate the cluster. The steps in the k-means algorithm. First, it chooses the k number of objects as randomly from the set of n objects. These k objects are treated as centroids or center of the gravities of k clusters. Step number 2. For each of the remaining objects, it is assigned to one of the closest centroid. Thus, it forms a collection of objects assigned to each centroid and it is called a cluster. Next step, the centroid of each cluster is then updated by calculating the mean values of attributes of each object. The fourth step, then assignment and update the procedure is until it reaches some stopping criteria, such as the number of iterations are completed, centroid values are remain unchanged, or no assignment or no data movement. The input for this algorithm, D is a dataset containing n number of objects, K is the number of clusters. Output from this algorithm, a K set of clusters will be the output. Step number 1, randomly chooses K objects from dataset as the initial cluster centroids. Step number 2, for each of the objects in the dataset D, we are going to compute the distance between the current objects and the K cluster centroids. Assign the current object to the cluster to which one is very closest. Third step, compute the cluster centers of each cluster. This will become the new cluster centroid. And then repeat the step 2 and 3 until the convergence criterion is satisfied. Here objects are defined in terms of set of attributes. Capital A equals to A1, A2 up to AM, where each A is a continuous data type. Distance computation, any type of distance computations can be used, or cosine similarity. Minimum distance is a measure of closeness between an object and the centroid value. Fourth one, mean calculation. It is the mean value of each attribute values of all the objects. Convergence criteria, any one of the following termination condition must be satisfied. Number 1, number of maximum iterations permissible. Second, no change of centroid values in any cluster. Zero movement. Fourth one, cluster quality reaches to a certain level of accuracy. Illustration of K-means algorithm. Here 16 objects with two different attributes A1 and A2 are given in the left hand side table. The values are available. So we are going to plot the values in the graph. As a scatter graph, it has been given. In the x-axis, A1 attribute A1 is given. The y-axis A2 is given. Suppose for the first data item 6.8 and 4.6. 6.8, 4.6, correspondingly we are going to plot a dot on the graph. Now we have arbitrarily we have chosen the centroid value for all the clusters, all the three clusters. Arbitrarily chosen values are 3.8 and 9.9 is considered as a centroid value for the cluster 1. 7.8 and 12.2 is considered as a centroid value for the cluster 2. 6.2 and 18.5 will be considered as a centroid value for the cluster 3. On the right hand side of the screen, it is shown the clusters. Three clusters are given: C1, C2, C3. C1, and in all the three clusters, one data object has been circled in red color. That is a centroid value, initial centroid value arbitrarily chosen by the user. That is shown in the red color. Other data points are shown only in the blue color. The calculation of new centroids of the three clusters using the mean of the attribute values of A1 and A2 is shown in the below table. The cluster with the new centroid value is also shown in the figure. Now new centroid values have been calculated for the cluster 1, cluster 2 and cluster 3. For the cluster 1, new centroid values are a 4.6 and 7.1. For the cluster 2, 8.2 and 10.7. For cluster 3, 6.6 and 18.6. So in the right hand side figure, old centroid values are circled in black color. New centroid values are shown in red color data points. The next step is we are going to reassign all the 16 objects to the three clusters by determining which centroid is closest to each one by calculating the distance function. This gives a revised set of clusters as shown in the figure. So note that point P moves from cluster C2 to cluster C1. The point P earlier it was in cluster 2. After calculating the mean value, again we calculate the distance, then it is moving from cluster 2 to cluster C1. So the near to that point letter P has been printed in the cluster 1. The newly obtained centroid values after second iterations are given in the table. Note that the centroid C3 remains unchanged, where C2 and C1 changed it little. With respect to the newly obtained cluster center, 16 objects are reassigned again. These are the same cluster as before, hence their centroid also remains unchanged. Considering this as a termination point, the K-means algorithm will stop here. Hence the final cluster is shown in the figure. The right hand side we can see the final cluster. Some of the notations used in this algorithm: X is an object under clustering, small n the number of objects under clustering, capital C I the ith cluster, that is I value is 1 means C1 and the cluster 1, cluster 2, cluster 3 like that. Small ci it is the centroid of the cluster capital Ci, that is cluster 1, and Ni means the number of objects in the particular cluster, that is cluster 1 or cluster 2. Small c denotes the centroid of all the objects. K stands for the number of clusters. In the k-means algorithm, how the value of k is determined. The k-means algorithm produces only one set of clusters for which user must satisfy the design number of k and design number k of clusters. In fact, k should be the best guess on the number of clusters present in the given data. Choosing the best value of k for a given data set is therefore an issue. So we may not have an idea about the possible number of clusters for high dimensional data and for data that are for scatter plotted. Further, possible number of clusters is hidden or ambiguous in image, audio, video, and multimedia clustering applications. There is no principled way to know what the value of k must be. We may try with the successive value of k starting with 2. The process is ended when two consecutive k values produce more or less identical results. Normally, k must be less than or equal to n, and there's a heuristic to follow the k more or less equal to square root of the n. In the k-means algorithm, usually there is some objective function to be met as goal of clustering. One such objective function is sum square error, denoted by sum of squared error and defined as SSE equals to sum of I equals to 1 to k. X is the element of capital Ci, x minus Ci whole square. Here x minus Ci denotes the error if x is in cluster Ci with the cluster center small ci. Usually this error is measured as a distance norm like L1, L2, L3 or cosine similarity. When k value equals to 1, the SSE value is 62.8 and k value is equals to 12.3. So that from this table we can find the optimum value of k. It is observed that the k-means algorithm terminate whatever be the initial choice of the cluster centroid. It is also observed that initial choice influences the ultimate cluster quality. In other words, the result may be trapped into the local optima if initial centroids are chosen properly. One technique that is usually followed to avoid the above problem is to choose initial centroid in multiple runs, each with a different set of randomly chosen initial centroids, and then select the best cluster. However, the strategy suffers from the combinational explosion problem due to the number of all possible solutions. For example, there are O of 10 to the power of 10 different ways to cluster 20 items into 4 clusters. Thus, the strategy has its own limitation is practically only if the sample is negatively small or k is relatively small than compared to n. Normally, Euclidean distance is the best measure when the object points are defined in n-dimensional Euclidean space. Other measures, namely cosine similarity, is more appropriate when objects are of document type. Further, there may be other type of fraction measures that are appropriate in the context of applications. Thus, in the context of different measures, the sum of squared error of a clustering can be stated as under data in Euclidean space. Sum of squared error formula has been given. Data in Euclidean space L1 now, the Manhattan distance also, the sum of absolute error also has been given in the screen. Suppose a set of n document objects is defined and document term matrix is shown like this. Here the objective function which is called a total coefficient can be denoted as TC value. This also can be defined. Cohesion is nothing but the strongest or the bonding between the data items. Bonding or strongest relationship can be defined as a total cohesion so that it has to be maximized. The type of objects under clustering. The k-means algorithm can be applied only when the mean of the cluster is defined. The cluster mean of a cluster capital Ci is defined as Ci equals sign 1 by Ni, sum of x is an element of capital Ci x. In other words, the mean calculation assumes that each object is defined with numerical attributes. Thus, we cannot apply the k-means to objects which are defined with the categorical attributes. More precisely, the k-means algorithm requires some definitions of cluster mean exist, but not necessarily it doesn't have as defined in the above equations. When sum of squared error is used as an objective function and the objective is to minimize, then the cluster centroid is the mean value of the objects in the cluster. When the objective function is defined as sum of absolute error, minimizing the objective function implies the cluster centroid median as the median of the cluster. The above two interpretation can be readily verified in the next slide. The time complexity of the k-means algorithm is expressed as T of n equals to O of n multiplied by m into k into L. N is the number of objects, m is the number of attributes in the object definition, k is the number of clusters, L is the number of iterations. Thus, the total storage complexity also can be calculated. N by m space to store the objects, n into k space to store the proximity measure from n objects to the centroids of k clusters. The k-means algorithm is very simple and can be used for a wide variety of object types. It is also efficient both from storage requirement and execution time point of views by saving distance information from one iteration to the next. The actual number of distance calculations that must be made can be reduced. The k-means is not suitable for all types of data. For example, k-mean does not work on categorical data because mean cannot be defined. K-means algorithm is having some problem clustering data that contains outliers. When the SSE is used, sum of square error as objective function, outliers can unduly influence the cluster that are produced. More precisely, in the presence of outlier, the cluster centroids, in fact, not truly as representative as they would be otherwise, it also influences the sum of squared error measure as well. K-means algorithm cannot handle the non-globular clusters. K-means algorithm not really beyond the scalability issues. We can learn the variant of partitioning algorithm called K-Medoids algorithm. We have learned the K-means algorithm is sensitive to outliers because an object with an extremely large value may substantially distort the distribution. The effect is particularly exacerbated due to the use of the sum of squared error as objective function. The K-Medoids algorithm aims to diminish the effect of outlier. The basic concepts of this algorithm is to select an object as a cluster center instead of taking the mean value of the objects in a cluster. We call this cluster representative as a cluster medoid or simply medoid. The step 1 initially it selects a random set of k objects as a set of medoids. Then at each step all objects from the set of objects which are not currently medoids are examined one by one to see if they should be medoids. The k-medoids algorithm determines where there is an object that should replace one of the current medoids. This is done by looking at all the pairs of medoid and non-medoid objects and then choosing a pair that improves the objective function of clustering the best and exchange them. The sum of absolute error function is used as an objective function. The CM denotes the medoid. Capital M is the set of all medoids at any particular instant. X is an object belongs to a set of non-medoid objects. That is, X belongs to some cluster that is not a medoid. For a given set of medoids at any iteration, it selects the exchange with its minimum sum of absolute error. The procedure will terminate if there is no any change in sum of absolute error in successive iteration. This k-medoids algorithm is known as partitioning around medoids. So illustration of this partitioning around medoids. Suppose there are 12 objects, capital O of O1, O2, O3 up to O12, and we are to cluster them into 4 different clusters. At any particular instant, 4 clusters, capital C1, C2, C3, and C4, shown in the following screen. Also assume O1, O2, O3, O4 are the medoids in the clusters of C1, C2, C3, and C4 respectively. For this clustering, we can calculate the sum of absolute error. There are different ways to choose a non-medoid object is to be replaced any one of the medoid object. Out of these, suppose if O5 is considered as a candidate medoid instead of O4, then it gives the lowest sum of absolute error. Thus, the new set of medoids would be O1, O2, O3, and O5. The new cluster is also shown in the following screen. The partitioning around medoids. Look at the left-hand side diagram. Left-hand side diagram. So O1, O2, O3, O4 are the medoids of the respective clusters. In the right-hand side, so instead of O4, O5 has been replaced. So O5 becomes the new centroid of the C4 cluster. Partitioning around medoids algorithm is a procedure of iterative selection of medoids and precisely given in the following algorithm. Input is database of objects containing all the objects in the dataset D. K is the number of desired cluster. Output from this algorithm will be the set of key clusters. Step number 1, arbitrarily select the K medoids from the dataset D. Second step, for each object Y not a medoid. Then iterate the following statement. For each medoid Oj, do the let M is equals to O1, O2 up to OK set of current medoids. M dash is the center of medoid, but it is going to swap. Then calculate the cost. Cost is nothing but between the Y and Oj. Sum of absolute error is calculated. Then end of to for loop. Find the OI and OJ for which the cost is which one is smaller. Replace the OI with OJ. Accordingly, update the set M. Repeat the step 2 to step 8 until the cost is less than or equal to 0. Return the cluster with M as the set of cluster center. The comparison between the k-means with the k-medoids algorithm. Both algorithms needs to fix the value of k, the number of clusters prior to the execution of the algorithm. Also, the particular algorithm arbitrarily chooses the initial cluster centroids. The k-medoid method is more robust than k-means in the presence of outlier because a medoid is less influenced by outliers than a mean. Then second point, time complexity of partitioning around medoid. For each iteration, partitioning around medoid consider k multiply n minus k pairs of object OI, OJ for which a cost of OI, OJ determines. Calculating the cost during each iteration requires that the cost to be calculated for all the other non-medoids in the data set. There are n minus k of this, thus the total time complexity per iteration is n into n minus k squared. The total number of iterations may be quite large. Applicability of the partitioning around medoid. Partitioning around medoid does not scale well to a large size database because of its computation complexity. There are some variants of partitioning around medoid that are targeted mainly on large size datasets, Clara, clustering large applications, and Clarence, clustering large application based upon randomized search. It is an improvement of